here. Okay. So is there any question about anything? So do you have any question about the, what is today due? So this is for the previous week. So I go to my course content. Should I just remind you where you can find all of the things that we are using for lectures? So one more time, if I go to the files over here, so then you can open the lecture notes. As you see, there are many of them. So you have either just you need the blank version of your lecture note, so you can find it over here. I put the entire lecture note from the beginning. I have several students who just returned to the class, means they were just somehow quiet for many reasons. So I will say it's just really 4 of them. So that's why I put the entire lecture note right over here. So if you have missed all classes from the beginning, or you have had some part of the lecture or not all of them, so the chapter 1, 2, 3, 4, 5 is just really the linear algebra part. And then when it says A something is just the differential equation part. And then, so for example, here is just what we are doing today. So if I can just make my pointer. Usually is right over here. No, it's not. I don't find my annotate. It's just, it's okay. So anyway, so you are in a 3.2 today, which is a mixture problem. And then your chapter 4 is uploaded too by 4.4. I think this is just the last one, but I will post the rest of them. And then if it's filled or it's after the Zoom meeting, is just down there. And then this is where it is. This is in the file. Okay, so this is in the file lecture notes. And then if you click on that Zoom meeting on the same files, this give you the YouTube or whatever is just the Zoom meeting. We have had 3 sections, so that's why we have 3 videos right over here. The only thing is I need to make sure this is not public, so that this is just should not be public for now. I don't know how do I make it. For now I make it unlisted. Whoever have the link, you can do it. So this is for us only, and that's just the lectures that we have had in the last 3 sessions through this Zoom meeting. And again, that was just all in, if I can bring this one down, that was all in the files. In your files, you can find all this information, including your quizzes solutions, your group work solutions, the test solutions, and then lecture note solutions. Okay. Do I have anything in chat? Not yet. Okay. So then as I said, we are just doing the 3.1 today, which you need to go to the files, and then the lecture notes, and we have a 3.2 because we haven't finished it last time. I'll try one more example today, and then we can move to the chapter 4. So these are all what is differential equation part, right? So we are doing the differential equation part, and we have finished the linear algebra by exam number 2. So the rest of the class is the differential equation and the connection between linear algebra and differential equation. So if I want to see what's the plan for today, first of all, I have to finish the previous class, and then I go to the course content, and I see, since we are in week number 11, and that's just the plan for today, right? So the plan for today is to cover introduction to the linear differential equation, which one more application of the mass spring, and just homogeneous linear differential equation, how to get the general solution, and later how to get the particular solution. So there are some videos which is for the YouTube videos, is not our videos, it's just really in general. If you need to make more, if you need to have more examples, you can just go and see that videos. Otherwise, you can just click on the Zoom meeting that I put it in the files and see the meeting, and then post your question on discussion board. And then group work number 13 is the only thing which is due tonight. And I have deleted group work number 14 because that was just really something that we don't cover here. And then you will have one quiz on whatever we have covered on the 8th. Okay, so this is the plan for this week. One more thing that I need to really make sure we are in the same page. You told me to make the quizzes to be available after the class, not before the class. Then the due day. So let's say the display, that was a problem last time. We got many emails for this part. Okay. So are we happy about this time? So I'm going to make this one to be after the class. So this should be about what is the after class time? Maybe what is this? Start at 11, we finish at 1, so I will say 12:30 is just the time. But again, you need to email me because this is what we decided last time. 12:30 and 1:30 is just really when this really entire quiz disappear. So this is set to be available at the end of the class. In general, it takes really 5 to 10 minutes to finish it. It should not be more, okay? So it's really the same thing that we have done in all of our classes. It should be 10 to at most 10 minutes class. And then since you need time to scan and to upload it for me, so I will just give you extra time, but that's just really 1:30, and it should be finished really quicker, a lot quicker, because as I said, it's really 10 minutes. And then this is just really nothing. The quiz is already ready for the Wednesday, and that's it. Okay, so this is the setting we have had last time. We are all happy about being after class, better than before the class. And then you see which topic you need to study because of the title, right? So when it says quiz number 9, but since you have your lecture note on your hand, it's not really hard to find out, but that's just really reviewing from whatever we have covered in the last class or the week before the spring break, okay? So that's what we have over here. And again, as we said, the plan today is just really to cover 2 sections of chapter 4 and to finish whatever we have left last time, okay? Is there any question about the setting the problem quizzes, the group works, discussion board thing? Is there any question for me?
Somebody in the chat said that you changed the time for the quiz to 12:30, but you have to change it to PM because it's stuck on AM. I don't know if you saw that already or.
No, I didn't. So this is the time. It was just really, but somebody says group work is, I mean, the entire, who was the chat? Can you repeat it? I think it was Isaiah.
Oh, it says week 11 isn't on Blackboard.
It's not, huh?
Oh, week 11 is was spring break.
Mm-hmm. But I just continued 11 to be this week. So let me just say, this is 12:30
PM.
Has to be PM. And then this is PM is fine. Okay, so this is perfect. And what was the other one? The week is not available. Okay, so if I go to the course content one more time, and then this is week 11. Permit user, thank you. You are right. How about the other weeks? Do you see all the other weeks, Isaiah? Okay, perfect. Thank you. Okay, so that was a good point. It's not even there. Any other question? Any other question? Okay, so let's continue the lecture. I mean, we have had it, just review quickly. This should not be there. Let me close your name over here. Make this one to be bigger. Okay, and then review what we have had last time. So there are a few application problems here. I think we have covered one. It was just falling body. This is the second one, which is mixing problem, and we will have the third one today, which is massive spring acceleration. So this is what we need to remember always. So when there is a tank, or there is something that has some liquid inside, so this is just about what is the concentration of the substance inside the tank. So what do we have is something which is going in, and then we just have a rate inside, and then we just have a rate outside, and then what is the concentration going in, what is the concentration going out. So this is just the notations. So rate of the flowing, rate of the flow out is called R sub 1, R sub 2. A concentration is C sub 1, C sub 2. And then the differential equation that we got last time, and that's just really what we need to remember. What is the differential equation, or the formula to just get the this type of mixing problem? Then is just really what you need to remember. Otherwise, the process we have explained why it looks like that, and that's just, I will say, for math measures is required. For if you are engineer, all you need to know what's the equation corresponding by this mixing problem. And again, the X is the amount of substance that we have in tank at time t, when some water or just liquid is coming or flowing in by rate R sub 1, and is flowing out by rate or R sub 2. Okay, so that's just really the equation that we need to remember. We have started, this is a process of why the formula looks like that. So we just need to know, in order to solve such this differential equation, since it is the application of first order differential equation, so we have to have always like this y prime plus a function in terms of x, y, and then eq of x. So this is the what we call first order differential equation, and it looks if a nice or a standard first order differential equation. So then how do I solve it? We have to get the integration factor, which is e to the integration of px dx, and then we multiply both sides, and then the next step is you integrate both sides after calling the left side product of two functions. Okay, so this is just really a simple problem. Why? Because the differential equation is given to me. All I need to just do is processing step number 1, what is the mu, step number 2 to multiply, and step number 3 to integrate both sides. So this is what we have had last time. Again, because the differential equation is given to you, you don't have to worry about how to set the problem. And then we got the P of t is just really this, and then the Q of t is this, and then so the integration pt is just really e, which by multiplying both sides I will get this really the product of two functions on left side, derivative, and when I integrate both sides, derivative and integration cancel out always. So then you have to just find out what is your x, then you just have to keep x here and divide both sides by the factor which is making negative, and that's just what we have had. I think we did not answer the question because we stopped, it was at the end of the class. So we did the process of integration again, or we solved basically the differential equation. And because we have had initial value, even we could get what's the constant, but we stopped there, but we didn't answer the question, because the question itself, if I go back on top, it says consider a large tank holding 1,000 liter pure water. So means the concentration is 0. And then you have to flow rate for just 6 liter per minute. And then rate out is the same, 6 liter per minute for flow rate out. And then concentration of this at the beginning was 0.1. The question was when, so means the t means the time, the concentration is going to be this much, when the concentration is going to be this much. So for now we did not get the solution, we just got the solutions to the differential equation. The question is when this value is going to be, one more time, I don't know, what was it, let me go back top, 0.05. 0.05 equals, I factor the 100, 1 minus e to the negative 3 divided by 500 t. So then just really what's the t? That's the question. At which minute, or let me go back, I don't remember what was the time unit. Was minute, yeah. After how many minutes the concentration is this much. So then this just really divide both sides by 100. And it's a little bit algebra, huh, to get the solution. It was negative, I'm going to make this one entire negative, and then I'm going to natural log both sides. So what is 1 minus this? 995, is it true? Did I miss 1 0? Yes, I did. There was 2 zeros. So that makes it another 9 over here. Is it true? Natural log. Natural log. So I have 500 negative t equals natural log of 9995 divided by negative 3 multiplied by 5. This cancel out. And then it is whatever. Okay, so you just put it in your calculator. What is 5 times natural log of 0.995? Let me see. I think I have the number. This is just the algebra. I think for this equation, I have had oh, that was 500, huh? This is 500. And I got, you can just try it on your calculator. This is what I got for the time. Okay, make sense? So this was left from last time. Now we have a problem to start from the blank. Okay, so this is just really the time that we will have the concentration of 0.05. Okay, so if the algebra is wrong, you can just check your calculator, because this is just really the process that we need to do, and that's not really hard. So let's just start this problem from the blank. If there is a tank, initial volume is going to be 600, and then the solution has 1500 grams of the salt. So means your initial X at the time of 0 is 1500 grams for the salt. A solution with the 5 gram per liter. So 5 gram per liter. So 5 gram per liter is just your concentration at the beginning. What was the rate? The rate is going to be 6 liter per minute for flowing into the tank. The mixture follows out the rate of 3 liter per minute. That's just your R sub 2. Find the concentration of the solution after 1 hour. So what is X after 1 hour? So since it's given by minute, so is what is X after 60 minutes, right? So because it's given by minute, 1 hour means 60 minutes. So this is what the question asked me to do. Again, the part that I need to really know based on what the differential equation of this mixing problem is this. This is going to be my main differential equation that I need to substitute whatever I have and solve the what is linear, first order linear differential equation by the method that we have learned in previous section. Previous chapter actually, because it was in chapter 2. So as you see, it's just really putting the numbers. R sub 2 was just 3, and then R sub 1 is minus R sub 2, so it's 6 minus 3, and then the initial volume is given. So R sub 1 is given to be 6, and then C sub 1 is given to be 5. So this is my differential equation that I need to solve. So it's just one simple calculation to see or to simplify that 3, and that's just really what we need to solve as a first order differential equation. I just remind you one more time. So first order differential equation has, if it's X, so this is X prime plus a function in terms of the T, and then I have X, and then I have a function in terms of the T. So this is a first order differential equation in standard form. And then if this is just the integration factor, so I have to remember because my input is just T, right? So this is going to be e to the integration of P of T dt. That's what we need to find out. So that's just my, what is P? This is going to be find integrating factor, which as I said is going to be pt dt. So this is 1 plus t plus 200 dt, and that gives you natural log of t plus 200, and that is t plus 200. Fine. Step number 2.
Can we get a minute to write some of this stuff down?
Yes. Ready?
Yes.
Okay. You multiply both sides by that mu, which was t plus 200, and okay, so that was just dx divided by dt. This is t plus 200. That's not good, right? I have to just make it in the same size. That was better. So this is, the middle one is t plus 200 times 1 t plus 200, and then x, and this is t plus 200 times the 30. This by this simplify, and that is, as we said, is going to be always multiplication of x and mu of t, sorry, x and mu of t. So this is x and this is mu of t, which is t plus 200 derivative. And the other side is just 30 times t plus 200. And then the next step is integrate both sides, right? And solve for x. Okay. This is going to be integration, and that is just integration by what is derivative cancel out. That's what is on the left side. And then on right side, I have 30 t squared divided by 2 plus 6,000 t, right? Plus constant of integration. I don't like it's too big, huh? Sorry, can I keep this one shorter by use substitution? It's better, huh? We don't have to have the big numbers. Here is 15. And then I think we do have initial value. Let's just come back to the top to see what is the initial value. I don't remember what was my initial value. I just divide both sides by t plus 200 to solve for x. I just divide both sides by t plus 200. T plus 200 to isolate my x. So this is what I have left. This is what I have left. Okay. But again, as I said, there should be something to find the t. I'm going to go back to see what was my initial value. It's right over here. X at 0 is 1500 gram. X at 0 is 1500 gram.
Could you slide up again of the value?
What was it?
I didn't see the value. Could you slide back up again?
I did. Okay.
Okay, thank you.
No worries. Oh, fine, okay. So then I have x at 0 equals 15, 0 plus 200, and then c divided by 0 plus 200, and that gives you 1500 gram. And that gives you, I don't know, I need to find out, right? So 15 times 2 is 30,000, and then c divided by 200 equals 1500. So that is giving me 1500 minus 1500, and then minus 1500 multiplied by 200. So C is minus 60,000, huh? Okay, not 30. Is it fine? My numbers? Are you agree? How many zeros do I need? 2 and then 5 zeros. Yeah. Okay. So then x of t is actually 15 t plus 200, and that's that big number, minus 1, 2, 3, 4, 5, 0 divided by t plus 200. Okay. Obviously it's okay. don't know why I did not change this in this file. 1, 2, 3, 4, 5. Okay, so this is my differential equation, but the question asked me something else, right? So this is the solution to differential equation. One more time to remind you the names. This was general solution, and this is particular solution to IVP, because that was initial value problem. But let's just go back to the question to see what it asked us to do. No way. Okay, it's coming. So what's the question? Question asked me to get this after 60 minutes. So what's the concentration after 60 minutes? So I'm not going to compute, okay? So it's just really what the question asked me, plug in X to be the 60. You can just go on your calculator and plug in X to be 60 to see what you get, okay? So that's just the question. This is just the question. Is there any question here? Do you have any question? And go ahead, please.
I just wasn't able to write down the particular solution.
Okay.
So after we get our equations, we just stop there.
It depends on what the question asked me, right? So we got the solutions right now. The question asked me what is X concentration after 60 minutes. So you do not stop, you just put your calculator, this number. I want to just try it right now because it takes time, but just plug in this value to be 60. Huh? And then see what's the number. Anyone has calculator to just quickly, because my phone is busy right now. If you have the number, you can give it to me. I don't think it's hard. Okay, you can find it. Any question about here? I'm going to leave really the next question for yourself because it's very similar to what we have done. Every single thing is given to you. You just need to plug in and find what is the X after 5 minutes. So X after 5 minutes is the question to find, but the process is really similar, okay? Any question for me? This was left from last class. So this was left from last class. We had no time to finish it. Move on. Any question, any comment? No? So the new section or the new chapter of chapter 4 is just really second order differential equation. We want to move to the second order differential equation one more time. We do have first application and then one good example of the what we call second order differential equation. Then we have a general way of solving, okay? So this chapter, as you see, is a long one. So there are 6 sections that we're supposed to cover, but I will tell you the entire six sections at the end briefly is going to be in one table. I mean, if you just really somehow, for this type of classes that we have right now, just really open book or open note exam, so you won't have any problem as long as that table is right in front of you, and then you can just write the solutions to this method of the solving differential equations. So it's just really based on one table. So entire chapter of 4 is briefly in one table. If I have that table, I can easily write the solution to the second order differential equation. So just one quick review what we have done by now. In chapter 2 was 2 type of differential equation. As long as it's separable, you just separate and integrate both sides. as long as it's in the form of y prime plus px y qx, you just get the mu, multiply and solve it, right? So this is just different, right? That was just first order differential equation or separable. So if these two are possible to do, we obviously do. So chapter 4 is second order differential equation. So it means you don't see prime. The highest that you see is just y prime, y double prime, sorry. So that's just a second order differential equation, which is a different method, a completely different method. But I will tell you, it's just really something like quadratic formula that you have learned and you are using always. And it's just really that much easy and just handy to solve the second order differential equation. Before getting to that point, to get the second order differential equation, the first thing that we want to see why we are interested to do second order differential equation, because there are many applications, right? Because there are many applications, and one of these application is just when you have a mass spring equation. So what does mass spring equation means? You have a spring and then something, some mass or some extra weight is just at the end of your spring. And the first thing is we just try to get the differential equation corresponding by this problem. And then when we get it, we just figure out, okay, this is a second order differential equation. And then we just, in this entire chapter, we try to solve this type of second order differential equation by two different methods. And that's just what the goal is for the entire chapter. Any comment for me? Someone must remind me the break time. Okay, so I think we are good to continue for now. So introduction to the mass spring. So what it is, you are having the spring, and then there is something at the end of your spring. It might have some extra forces, might not. It just really depends. So this is just the mass, and how much is moving to this direction is just the distance. And we are assuming right here is just the resting time for the spring. Okay, so right here is the spring, so it's stretching somehow. And then if we have had a just really basic physics, I know you have learned some physics, so this is just really the basic physics, that it says this type of motion is related to some differential equation, which is related to what is the spring elasticity. So what is the spring is just, where is it? Yeah. So the force by a spring is always minus a constant times the how much is just the changing. Okay, so it's right over here. So this is what the Hooke's law is when K is a constant. The K has a name, we call it, I don't know, stiffness. Have you seen such a, this name is fine, but as long as the equation, I'm pretty sure you've seen it somehow in your even higher school. What is the spring force? So it's K, which is the stiffness, and then is negative because it's always against of your force, and then multiply by displacement. And then one more thing that is just coming to this force is just damping friction. What is damping friction? Is just really multiply, is a proportion of velocity. It is a proportion of velocity, which that proportion or extra factor is called B, and then velocity is just the derivative of your displacement. So displacement is Y, so velocity is just the derivative of that displacement. So this is force number 1 that you see, force number 2 that you see. Force number 1 is coming from the spring, force number 2 is coming from friction. And then you might have possible external forces too. You might have possible external forces to move the spring, to stretch or to shrink your spring. So based on what we have learned from the physics, I don't really expect you to remember this much rule from the physics. It's just really to tell you how is applicable, very simple laws that we've seen it in your what is the differential equation course, and you've seen it in your basic physics. So then your force, as we know by the second law of Newton, is going to be is mass times acceleration. And then you have had the whatever is just your spring force, which is negative because it's against of your motion. And then whatever is your friction force, because this is just again negative because it's against of your motion. And then you have had positive external forces if you are helping to stretching or you're shrinking. So that's just what or how you can make a second order differential equation, because your acceleration is going to be second derivative of your motion or your displacement. And then you have had y, and then you have had y prime, and that's just really a second order differential equation, which nicely we write it in this form. Okay, so this tells us that type of motion, which is mass spring, is going to be just corresponding by each time you do all this process is going to be a second order differential equation, which M stands for mass, D stands for the friction proportion, K stands for stiffness, and then F is just really whatever is your external force. Any question? Again, because we haven't learned how to solve it, we will just learn in the next two sections how to solve it. So it's just really having the equation and simply check whether something is solution or not is the only goal of this section. So the only goal for this section is that's just second order differential equation. It is a linear. All numbers of M, B, and K, they are all numbers. There is no function left. So these are all constants by y double prime, by y prime, and then y. They are all constants of M and BK, because if they are not constant, we have different method to solve it. And that's just a corresponding differential equation for this one. Okay. So again, I don't know still how to solve it. I just can give you the solution, and then you can check whether it is a solution or not. So for example, it says verify if your B is 0 with no external force. So if external equals 0, then the equation has the solution of this form. So means sine and cosine is going to be the solution of the differential equation when there is no B and when there is no external force. So it's only your stiffness and your K times Y. And that, I think if you have had physics, you've seen this omega to be square root of K minus M, but we just drive the formula here if you haven't seen it again. This is just to derive the formula. It looks like that. Again, this is just really solution number one, solution number two of the differential equation, which it says B must be 0, which it says F must be 0. Okay, so this is really given in the problem, set these two to be 0. So I have M y double prime plus ky equals 0. And my goal is to set y1 is a solution. All I need to do just really plug in back, huh? So I need to say, okay, so what is my first derivative of this? Is cosine minus of sine. And what is my second derivative of this? Is sine, which is cosine. And by chain rule, I have to multiply by another omega outside. And then I have to plug in back right over here. Plugging back right over here. So to see whether I get 0 or no. So I have M, and this is going to be minus W2 cosine of WT and plus K cosine of WT, set it equals 0, So I will factor the cosine of WT. So what I have left is m times omega to the second plus k equals 0, which means, is it fine by now? This says where the omega, sorry, equals by this is going to be entire 0. That's true, right? So this is really true because you have to set this one equals 0. Okay, you have to set this one equals 0, means you have to move it at the other side, divide it by m, and then square root both sides, and that would be really what it is, right? Is that okay? You can similarly just do the other one, which is the sine, okay? This is a really good one because we will see what's the solution or how the solution is going to be in terms of cosine and sine soon, and then you will see, because the solution was just really complex numbers. That's why the cosine sine is coming through. Otherwise, it shouldn't be. It should be really constant. Okay, so you will see in 4.4 why this is in this form. One more time. Was it enough time to write down? Can I move on? Yes.
Yeah, it's fine.
Okay, so then the next one, it says you have this solution this time. So that's just supposed to be the solution to same differential equation. The numbers are given to me, right? So this time again, there is no external force. The mass is 1. I think it was kg from the beginning. And then the B is 6. And the K, or stiffness, is 25. Okay, so the question is, again, I don't know how to solve it. All I can do as this step is just really verify it. So M is 1, and then B is 6, and then K is 25, and then there is no external force. The whole idea, or the whole goal, is plugging back. It's like really like algebra. So if this is a Y, plugging back to see whether it's satisfied or no. So then it's just a little bit calculus, huh? I have to, I should turn off this one because it changed my, okay. So I need the first derivative of this function by the product rule, derivative of first times second plus derivative of second times the first. Derivative of second is minus 4, and then I have e to the negative 3t, and then I have sine of 4t. And then one more time, derivative of first times second, derivative of second negative 3 times, that's just plus 12, okay? Derivative of second times first. Agree? Minus 4 times 3 is 12 e to the negative 3t. This time is derivative of this, okay? So derivative of this, I'm writing over here. Derivative of this, I was writing over here, okay? So this is really calculus. Then derivative of sine is cosine. And 4 times 4 is 16 e to the negative 3t. Okay, one more time. I just want to make sure my derivative is correct. Derivative of e negative t, this is the same thing. Derivative of cosine is sine negative, and then in the next step, this gives me positive 9, and this is the same thing. This gives me, because it's cosine, negative to negative is plus 12, and this is okay. Next term, this is again 12 positive, and then sine is just positive, so it stays negative, 16 negative 3, okay? So that's it. I just need to plug in. It just really what it says. Y double prime, I just write it with the blue, which is 9 e to the negative 3t cosine of 4t plus 12 e to the negative 3t sine of 4t and plus 12 e to the negative 3 sine of 4t. Maybe it was easier to add the like term. Sorry, I'm going to erase and add the like term first. Sorry, I didn't see there are some like terms over here. So this is going to be 9 minus 16, right? 7 e to the negative 3t cosine of 4t. And the other one is 12 and 12, so it's 24 e to the negative 3 sine of 4t. Then the y prime is minus 3 e to the negative 3t cosine of 4t. And then this is minus 4 e to the negative 3 sine of 4t. Okay. And then plus 25. And I just make it maybe green. E to the negative 3t cosine of 4t. Okay, am I right by now? Is it okay by now? We will figure out if there was any mistake, so you won't get the 0, right? So this is a cosine, this is a cosine, and this is a cosine. So I have had negative 7 minus 18 plus 25, many of the cosine 40. And then for the sine, this is a sine and this is a sine. And I have had 24 and minus 24 e to the negative 3t. I'm going to factor e to the negative 3t. I don't want to repeat all the way. All of them has e to the negative 3t. Let's just keep it all the way outside. Then we don't have to repeat it again. That was for the sine of 4t. And this is closing, and that's just really 0. And that's it. That's what we're supposed to show. I mean, it's just really calculus or algebra than differential equation. Why? Because we still don't know how to solve the differential equation. But we will learn soon. Is that fine? Should I wait for you? Anyone needs more
A
time?
couple of seconds.
Okay.
Okay, I'm good.
Okay, so this is it. This is just really start point for this section, is reminding you in general, whatever is this mass spring is going to be whatever is just the m, it's your mass times the second derivative, and the whatever is just your b value times y prime, and whatever is your k stiffness times the y equals by this. So I have to remember this is just really what I want. So if you have A1 and then A2 and then A3, to be a linear differential equation, these are all constants. So for now, these are all constants for this chapter, the entire chapter. And then since it's second order differential equation, so then you have the highest degree has to be second order, but one of these could be zero, right? So this A1 is non-zero because that's why it's the second order differential equation, but the rest of these constants or numbers can be zero. This is in general what we call first order differential equation, sorry, second order differential equation, okay? So I'm going to stop here for a break time, and then I'll just continue to give you the techniques of solving differential equation. Then we don't have to worry about how to solve. And again, the entire chapter at the end is going to be briefly in one simple table. Okay. So for
Could
now,
you leave up that thing you just left off on if we're going on a break?
the last page or the page before?
Yes, please.
This is not the. Okay. So let's just say we'll start at 12:05. Okay. Come back at 12:05 to continue. But I'm here. If you have any question, you can ask me. Do you see how the differential equation part is a lot easier than the linear algebra part?
Yes.
And you were really lucky that we have done that part at the beginning in the class. And then when we transfer to this, because for 2240 is the other way. They have done the differential equation part, now is the term for linear algebra part. But in 2250, we do always linear algebra part. And I don't know what's the reason. It's just really, they are the same. At the end, we'll get to the same point, which is our chapter 9. Okay, so let's start again. What do we have? As I said, is for now linear differential equation, and for now is second order linear differential equation. Okay, so what does the second order mean? The highest degree of derivative that you see is the second order differential equation. Okay, so this is a second order differential equation, and there is a terminology of the homogeneous and non-homogeneous, which is really easy. If this right side, except whatever you have in terms of y or y prime or y double prime, the right side of the equation is all in terms of x. If you don't see anything, means it's just really right side equals 0, that's homogeneous. But if you see on right side something like x squared, something non-zero, so that's non-homogeneous. So this is easy to figure out which one is homogeneous, which one non-homogeneous. For all of the differential equation, we will solve always homogeneous one. So we just solve always what is the homogeneous, or we set it equals 0, and then we just take care of non-homogeneous. So anyway, it doesn't matter it's homogeneous or non-homogeneous, we have to take care of the homogeneous part first. So set it equals 0 always for any single problem. This is just really the process that we do. And then again, all of them are linear. So this is the second order linear differential equation. Linear means these are all first degree. So the y and y prime and y double prime, they are all first degree. So that's just for now for 4.2 homogeneous linear second order differential equation. Okay, and these are all constant coefficients. What does the constant coefficients mean? This is not in terms of x. These are just really numbers, as we have seen in the mass spring the problem. This is just really all in terms of constant for this section. Okay, for this section, for this chapter, entire chapter, not for the next chapter. So for chapter 4, we assume everything is linear, and we assume all the numbers or coefficients are really constants. Okay, so we don't have any function in terms of x. Basically, they are really all constants. Okay, and first thing that we have, we just guess, we wish that the form of solutions to be e to the r to the x, and that gives you what they are. Okay, so if we test or the process why this is true, then that gives you the actually the method of solving this differential equation. Okay, so what do I mean to wish? So if your y equals e to the rx supposed to be the solution of this differential equation, so means you have to plug in back, and that means you have to take the first derivative, you have to take the second derivative, and then you see what is left. Okay, so this is r e to the rx, and that is going to be, oh sorry, let me rewrite it one more time. The second derivative of this is going to be r squared e to the rx. Okay, so if I plug into the a, y double prime plus b y prime plus c, and again we are taking care of 0 on right side or just homogeneous for now. So this is a, y double prime was r squared e to the rx, and this is b, and then y prime was r e to the rx, this is c, and then y was e to the rx, and then you set it equals 0. So you can factor e to the rx, so a r squared left, b r left, c left. So I remember from the algebra, e looks like this. E to the rx is always positive, never gets 0. So means this never gets 0. So product is 0, means ar squared plus br plus c equals 0, which is really a quadratic equation. So this would be a solution if it's this, okay, e to the rx is a solution two differential equation if R is a solution of quadratic equation, whatever it is, just really AR squared plus BR plus C. Does it make sense? The claim was e to the Rx must be a solution. And then when we plug in back to this differential equation, we figure out that would be true if the R is the solution to the quadratic equation. And that's actually what we need to solve this differential equation. What we need to solve this differential equation is corresponding quadratic equation, corresponding polynomial of degree 2, and this is auxiliary equation. And this is characteristic equation, auxiliary equation, so that's just different names in different books. And that's really easy to find out. You see, if you have A right over here, and then if you replace y to the second by second degree of the R, and then B is right over here, and then you replace first order y prime by the first degree of the R, and then you have C right over here, and this is a zero derivative order, so that's just really y to the 0. Okay, so this is R to the 0. And that's why it's just really easy to write corresponding auxiliary equation or just characteristic equation. Okay, so that's what I need to know. If I know what is that's corresponding characteristic equation or auxiliary equation, I just write the solution to be in terms of this. So R must be the root of that polynomial. Then the solutions to differential equation looks like always e to the R times x. And it doesn't matter if it's a second degree, third degree, or fourth degree. That works always. So this type of proof that we have done over here, you could really keep going and just do this one to the second degree. And then if you take one more derivative, it gives you the third. If you go one more derivative, it gives you the fourth derivative. And you could really keep going. So that tells you this way of solving differential equation works for any order of differential equation as long as these are constants. As long as your coefficients of differential equation are only numbers, you can always solve corresponding polynomial like algebra. If it's first degree, second degree, or just fourth degree, you solve that corresponding polynomial and then you write your solution in terms of e to the power of solution R times x, and it works always. Okay, so this is what we call a differential equation with constant coefficient. So as long as there is a constant coefficients for any y prime, y double prime, y to the power of to the third order of the derivative, that's just always the method. Find corresponding polynomial and then solve for that and get the solution. Okay, so let's practice. Do I need to give you time to write down this part? This is really posted online. Should I wait for you, Joel?
Just like 15 seconds.
Okay. Who else is taking note?
Me.
Are you with me, or you need more time?
Just 1 second.
No worries. Okay, in general, does it make sense? All I need to do to solve this type of differential equation is the constant, write down corresponding polynomial. What does it mean, corresponding polynomial? All of those derivatives now is going to be just really power of your variable. And then you have a polynomial like really algebra, which you can solve it by any method. And then when you have the solution, e to the Rx is your solution to differential equation. Okay. Ready? This is the same as 2r squared plus 3r minus 5 equals 0. Is that okay? Corresponding polynomial means take out your y and then replace by corresponding power. So this is a y double prime, this is going to be r squared. This is y to the first derivative, so this is r to the first. So this is non-derivative or zero derivative, so then it is r to the 0. So you write corresponding polynomial as just really algebra, you know how to solve it, and then you get the solution to this one. What's the solution to this one if there is any? Which one must be negative? This one, huh? That is true, right? Am I right? So this gives me r is negative 5 over 2. This gives me r is 1. So what's the solution? E to the negative 5 over 2x e to the 1x. So that's the solution to differential equation. Easy, right? So the only concern that we have is entire just really 4 sections for us to say, okay, this is a polynomial of degree 2. It might have unique solution of 1 or it might have 2 real solutions. It might have 2 complex solutions. Okay, so that's why the chapter is getting long. Otherwise, the process is going to be always the same. Corresponding polynomial, solve quadratic equation, you get the solution. But the problem is it really 2 solutions? Perfect, easy. That's what we do. How about if it's repeated solution? How about if it is complex solution? So that's just really different sections of this chapter. Okay, move on. And then if you have any 2 solutions, remember, because you are solving second order differential equation, you get 2 solutions. So if you are solving third order differential equation, you must get 3 solutions, okay? So, but it's reminding us, if you have 2 solutions of this, sorry, highlighter. So if you have 2 solutions that we just got over here, so then any linear combination still is a solution. Any linear combination still is a solution. So this is a little bit linear algebra is coming through why these 2 must be linearly independent. So any linear combination of those is giving you really basis and then a span set. Okay, so that's just really, I will say, mild linear algebra that we have here. These two y1 and y2 are, oh sorry, this was y2. Y1 and Y2 are 2 linearly independent solutions, and then any linear combination of those means span set. So Y1, Y2 basically is the basis for your solution set. Okay, so if you use those concepts. Does it make sense? Do you follow me? You can write over here. Okay. And it could be IVP, initial value problem. Then you can take care of your constants of C1 and C2, right? So I'm going to go back and just at least make my general solution right over here because I didn't. So my general solution was C1 e to the negative 5 over 2x plus C2 e to the x. Okay, and then now, oh, let me give you time to write down. Now I want to just follow same process, this time take care of my constant. So this is my general solution. But if I take care of the initial value conditions and find out what is C1, C2, this is called particular solution, okay? Ready? Can you say yes? Anyone is ready?
Yes.
Yes.
One more yes. It's just 2 yes only.
Ready.
Okay. So maybe some of us is doing in the bed, maybe sleeping right now. Okay. So this is going to be, thank you. This is going to be 2, and then y double prime is r to the second, then r, and then minus 5 and set it equal 0. Okay. So then it's going to be really simple algebra. We are okay with that. So this is 1. This is, well, actually I've done it once, right? This is plus, this is minus. The only thing is I just need to take care of the, what is it? Is it exactly
It's
the same
wrong
as?
way. It's
Le-
4 plus 5 and r minus 1.
Oh, it's not the same thing, huh? So this
Yeah.
is plus, this is minus.
Yeah.
5r minus, so this is plus. This is minus. This is plus. Yeah. Okay. So anyway, that was really same thing that we have done on top. The only thing is it's the initial value. That's fine. I can just plug in, right? So what it is, remember the degree or the order of differential equation is the same number of initial value conditions you need. Okay, so if you have first order differential equation, you need only one initial condition to get the C or the constant or make particular solution. But if you have second order differential equation, you need 2 initial value conditions to get the C1 and to get the C2. Okay, so for the first one, it says y at 0 equals 0. Okay, this is the first one. For the second one, it says y prime. So I have to take care of my y prime first, right? So I have to know what is my y prime, because this is just really plugging the value of 0 at y prime, right? So derivative, and then derivative of this one. Okay. It's -1. Is that fine? So first one says basically C1 plus C2 is 0. So that's number 1. And then number 2, sorry, I should not put this arrow over here. That doesn't make sense, right? So this is number 2, which says -5, 2, C1 plus C2 is this. And then you need to take care of your C1, C2, okay? So you need to take care of your C1, C2. I am going to do it right now. 2 plus 5 is 7. So 7 divided by 2, so it's 2 divided by 7. Then C2 is opposite, huh? That says C1 is opposite of C2. So it's negative 2 over 7. Is that okay? Agree with me? Yeah, that's true. Okay, so this is my particular solution, which is going to be y equals c sub 1 e to the negative 5 over 2x plus c sub 2 e to the x and whatever, huh? So this is just what we call particular solution to IVP. Is it okay? Any question?
So for the particular solution, you just plugged in our C1 and C2 to the first equation we got, or we started with?
So this is my general solution, right? And then all I need to do, plug in y at 0 is 0, plug in y prime at 0 is negative 1. So then yes, I did plug in x equals 0 over here, the original one, and I did plug in the y prime to be 0, so it's just really this value is 0, this value is 0 equals negative 1 over here. And that gives you two equations, two variables, which you can do by elimination method or substitution. Does it make sense? Any other question from? Okay. Move on or no? Move on?
Yeah,
Okay. So if you remember, and I just mentioned over here, we are always looking for linearly independent solutions, right? So if this is dependent, we don't like it to keep it, right? So for example, if you have, if I go back over here, if e to the x is a solution for you, any scalar multiplication of that is going to be, I'm going to use the same letter that I have used. Any scalar multiplication of that is going to be just really linearly dependent, and it still is a solution, right? And if you have y2 is just e to the negative 5 over 2x, then any scalar multiplication of that is going to be dependent, and that is just still a solution for that one, and then linear combination of that one. So we don't like to have linearly dependent solution, because basically they are just really scalar multiplication of the original one, or just any linear combination of that. So just to remind you, that's really same story over here, same concept over here. Linearly dependent means you have a pair of functions are said to be linearly dependent if there is no way to be linearly independent, if there is no way to be as a constant multiplication of each other, right? So same concept. So if this is dependent, means they are a scalar multiplication. If it is independent, means there is no way to write as a scalar multiplication of each other, okay, when they are a pair. And then I think I messed up with so let me make sure I'm writing correctly. So it's linearly dependent. A pair of function of a1 and a2 is said to be linearly dependent on the even then it's just, this is independency, okay? So this is independency. If and only if neither of them is constant multiplication of them, okay? Linearly independent if they are scalar multiplication, they are linearly dependent. Okay, so exactly, I just made a mistake. So this is dependent. Sorry. Okay, so I have to fix it in my lecture note. This is independent. So independence means there is no way to write as a scalar multiplication. Dependent means they are a scalar multiplication of each other, okay? So this is the same concept that we've seen it. There is a test, there is a check to find out whether two functions are linearly independent. It's named Wronskian. It's really easy. Wronskian is a lot easier than even a scalar multiplication. But scalar multiplication, sometimes they are not clear, but Wronskian is always clear how to find or how to test whether they are linearly independent, okay? So Wronskian says, what do we call a Wronskian? Wronskian, to test linearly independency, says just put your function in first row of your determinant, and then the first derivative of that in second row. It gives you really a determinant, huh? So it gives you really a determinant. As long as that determinant is non-zero, they are linearly independent. I don't think we have any problem with this concept because we've seen this one, right? So we know determinant of the matrix non-zero means linearly independent. So that's really same thing. All I need to do, the first column, sorry, the first row is the functions itself. The second one is just what we have derivative of those functions. As long as they are non-zero, this is perfect. These are linearly independent. So if I want to practice, I will really practice something which is not clear, right? So for example, if you have something in terms of sine and cosine, and the question is, because there is many relation between sine and cosine, so the question is whether these are linearly independent or dependent. So for such these functions or any of these combination of sine or exponential function or natural log function, so to make sure they are not linearly dependent or they are not a scalar multiplication of each other, Wronskian is really a quick way. So what the Wronskian says, if you want to make a Wronskian of two functions, all I need to do, make a 2 by 2 determinant. Why? Because I have two functions. One is sine, the other one is cosine. This is my first row. Then my second row is the derivative of sine and cosine. So derivative of sine is here, derivative of the cosine is here, okay? So this means I have had the sine of x, and then I have had the cosine of x, and then I have had derivative of sine, which is cosine, derivative of cosine, which is negative sine, determinant is minus sine square, and then minus cosine square x. I can factor a negative, that would be sine square plus cosine square, and all we know is this is negative 1. As long as it's non-zero, then y1 and y2 is linearly independent. And that's it. It's really quick and nice way of checking when they are functions, okay? So when they are functions, because when we have functions, the derivative makes sense, right? So if your solutions are functions in terms of x, so you can just first row to be functions, the second row, and it works for as many as functions that you know. So if you have 3 functions and you want to test whether it's linearly independent, you can just do it the same way, right? So again, this method is really great method because you can just really go and try for as many as functions that is given to you, and then you wish to test whether is whether is independence or not. You put the functions in first row, and then you go to the first derivative of this function, and then you go to the second derivative of this function, and then you keep going. Because it's determinant, it has to be square matrix, okay? So since it's a determinant, it has to be square metric, otherwise it doesn't make sense, right? So you keep going until you get the square matrix. So you have to go by this one less than the size of your matrix, because you have had n many, you go by the derivative of n minus 1. Since you have had too many, so you went by first derivative, one less is always. And as long as the determinant is non-zero, this is linearly. Oopsie, I shouldn't make doubles. Sorry, this is really important to know. The other way doesn't work. But really this way. This is really important to know. It's just one way. If determinant is non-zero, they are linearly independent, but there are many linearly independence which not necessarily works to the other way, means the determinant non-zero. Okay. It is a one-way theorem. It doesn't work both ways. Okay, so this is what we need, right? So 2 functions are linearly independent if and only if the Wronskian is non-zero, at least for 1x. And then 2 functions are linearly dependent if and only if this is non-zero for all of them. Okay, so independency means non-zero, dependency means 0. Okay, so this is a typo. This has to be equal. These are the things that I will fix it in the original lecture note.
Could you go back and explain your sine squared and cosine squared, like how you got that? You said it was the determinant of that?
Yeah, it's always determinant. You multiply this minus this.
Okay.
The Wronskian is a determinant. Wronskian is just a determinant of 2 by 2 matrices if you have 2 functions.
Okay.
Okay. So just remember this, if you have independency, if you remember from the previous linear algebra part, you need to have non-zero. If you have dependency, it has to be 0. Okay, so this is a typo, but that's just really important to know. This is at least, I mean, 1 non-zero works, but this is for all. So if it is 0, it has to be 0 for all of the values. Okay, so this you will see in the examples. What does it mean? So only 1x right over here gives you, if only 1x gives you non-zero, you are good to go. That's independence. But if you want to say dependent, you have to say all of x's gives you 0. Okay, so again, this is a really nice, easy test. If I just check it for 1x and the determinant is non-zero, that's perfect. We are just really saying these are linearly independent functions. Okay. And then if you have 2 solutions, they are, as I said, they are linearly independent solutions the way that we have defined. And then any general solution is just really linear combination of those. So there are a list of the functions to test or to practice this differential equation, I mean, this Wronskian method. And we have tested actually number 1 already. Okay, so we have tested number 1. It says determine which of these functions are linearly dependent or independent. And we have tested one of them. Can you really look at the function, tell me whether they are linearly independent or dependent? What do you guess, for example, for the B part?
Will it be linearly dependent?
Dependent? Independent? I have 2 different. Any other idea?
Well,
B Wronskian of x squared and 3x squared plus 1. So this is a determinant x squared and 3x squared plus 1 is sitting top. Derivative of x squared is 2x. Derivative of this one is 6x. Determinant is going to be this 2 multiply, which is 6x cubed, minus this 2 multiply, which is what is it? 2 times 3 is 6x cubed, and then minus 2x, huh? So this is going to be this by this cancel out, so it's minus 2x. Is that true? Okay. If this value is non-zero only for 1x, then linearly independence. It is, right? So I have just except x equals 0, all values of x's gives you Wronskian non-zero. So they are linearly independent. And actually, because there are two of them, it's not hard for 2, right? For 2 of them, as long as I can just really scalar multiplication, they are dependent. If not, they are independent. I mean, for 2, we have done really harder than this in the previous part of linear algebra, right? So for testing for 2, I don't think it's just really hard. Unless it's really like a sine and cosine, because there's many ways to write it by many trig equations. Okay. 5 minutes left. So let's just say this is, wow, the main thing left. Okay, no worries. That's good, because those are really connected. I don't want to left it incomplete. So the last part is connected. It's better to do all together. So this is going to be then part C, which is your function is just really similar to the solutions that we have done. So the way of the solutions for differential equation with the constants variable is always e to the something, is always e to the something. So it's just really the good practicing to see whatever we have done for the problems, and we got these solutions to the differential equation. I mean, this way of solution is not, it wasn't really exactly same solutions, but that's just really good to see they were all linearly independent, or there is no way to write one of them as a scalar multiplication of the other one. We were sure. This is just really testing the Wronskian. Derivative of this one is this, derivative of this one is this. Okay, so then you have 3 e to the 3x times e to the negative x minus e to the negative x times e to the negative 3x. Sorry, that was a negative. So this is giving 3 to the, how many x's? 2 x's. This is e to the 2 x's, so 4 e to the 2 x's. So, and this is non-zero. I mean, because e to the 2x never gets 0. Right? And that's it. So e to the negative x and then e to the 3x are both linear independence. I'm going to stop here. And again, because the next part, which is how many solutions do I get from quadratic equation, it's really clear, right? So how many solutions do I get from the quadratic equation? Either I get one unique solution or two real solutions or two complex solutions. So it's just really the way that we just need to separate or to write the solutions to differential equation. And then we stop here. Okay, so we do this one on Wednesday. Do you have any question? Do I have any question in chat room? Oh, I have so many things in chat. Okay, no fine.
When will we get our scores for our midterms back?
That's a very good question. I'm hoping by the end of this weekend.
Okay.
As I said, my goal or the idea is, as whatever you get on the my MATLAB stays mostly the same, unless you miss the points, and then I check your steps. That's my plan. Whether I can give you partial credit to bring it higher than what it says, but you can just assume whatever you got from my MATLAB is just your grade, unless you did better in your work. Any question? Any question?
So for the test, you look at the work that we've done compared to the answer, and that can increase your grade?
Increase. I'm hoping not decrease like at all. It's increasing.
Okay, thank you.
If you have really, I got really some emails. I'm just pretty sure at least for 2 students that I got from the email, there was a case that they got their number wrong to my MATLAB, but when they did the work again, they figured, okay, it was just really a computational mistake. That's why they couldn't get the credit. So that helps me a lot. So that at least for that 2 students, I have on top of my head, okay, so let's just check what she has done or he has done in the steps to see can I bring back the credit to that point, that problems. But if you have such a distinct, that helps me. Okay, so that helps me to save time. If you have done or you got wrong on my MATLAB, but when you read it on your work, you got it correctly. So if you email me, that helps me. At least I can just point directly to that problem. Otherwise, anyway, that's my job. I will check it.
I don't know if it was just me, but I had a hard time finishing. I didn't finish like several of the questions. I don't know if it was just that I wasn't working fast enough or I don't know. But I went back to my work with the write-up, and I hope I did better than I done the math lab, because for the math lab, I got like an F.
Okay. Any other comments?
Yeah, I was running out of time too.
Yeah, that happened to me too. Like it ran out of time on my first attempt, and I had barely finished like half of the problems.
Yeah, same here with me.
I also ran out of time. I didn't do 3 of them.
But you have done in your work, right?
Yeah.
Okay.
Okay, good. I'm glad it wasn't just me. I had time just to like write down most of the problems, but not really input the questions into MATLAB.
Do you think write down the problems takes more time? That's why you run out of time, or not? Just really the computation was just.
I think both, because I know for me, I can't do it just looking at the problem online, I have to write it out or see it like on a paper in front of me and then do the work under it?
You know what I've done, right? So I told you I just made the whatever the time was just computed by computer. So it was just really based on thousands of students doing that problem. They said, okay, so this test entirely takes, for example, 100 minutes. So I made it double. So I just say if it takes 100, then I make it 200 minutes. So that's the way that I decided about it. So I said computer is decided to be 100 minutes, so I made it double. So when I'm getting the feedback from you, and then that's just number one, I can just take care of your work more carefully. And then number two is just really don't trust computer anymore.
Okay, sounds good. So would you like us to email you that
It
we
helps
did
me.
better?
It
Okay.
helps me. So for now, I just remember Carolina is one of them.
Okay.
Right. So this is just because it helps me, but in general, I'm getting the feedback that is just all we can do, right? So we do the best, right? So this is all we can do, and you're doing great. Okay, so don't worry.
Okay, thank you.
Give me more feedback. Okay. Any other question for me? Okay, if not, see you again on Wednesday, and then don't forget about that. Practice a little bit to be ready for little quiz that you have always, and this time is online. Okay. Any comment for me? Yes, Brandon.
Is the quiz supposed to be on Blackboard?
The quiz. Which one?
And under week 11, right?
Yeah, quiz number 9.
Oh, because I don't see it under here.
Yeah, because it will be available at a certain time. We set it to be available always at the end of our class time.
Oh,
yeah.
All right.
And then it will be closed after 1 hour.
Okay.
Thank you for asking.
Thank you.
Any other question? Okay, so see you on Wednesday. Okay, take care. Bye.
Thank you. Have a good week.
You
Bye.
too. Thank
Bye.
you.
Thank you.
Bye-bye. Thank you.